Okay, now I'm recording. Okay, so share the screen. Yeah, just a sec. Okay. Okay, where's the? Oh yeah, here is. Okay, so yeah, so maybe yeah, so let me just write it down. Uh, okay, so if you have an elliptic curve here, yeah, so then I'm defining endomorphism, which is given by the doubling of the point. So then this yeah, okay, so the doubling will have something, but which you can actually write it as 3x square plus a by 2y. So yeah, so remember that this is m, 3x square plus a by 2y. So this is the slope of the tangent at p. So this m square minus 2x. So actually this is actually formula which we have, but we are writing in this form. And 3x minus 3x square plus a by 2y whole square minus y. So this is r2 xy. So basically, like it's just a homomorphism of the elliptic curve. So elliptic curve, remember that it's a group, it has a group structure, so it's a homomorphism of these two groups. So in the endomorphism means I mean, you know, the it's like group homomorphism from one group to this another. So okay, yeah, so this is how we define an endomorphism. This is an example. Huh? Okay, yeah, just give me. Okay, all right. So yeah, sorry about this. Okay, so yeah, I have this R1, R2. So it will be it will be nice to write these rational functions in a different way. So You see, so in E, which is in general, so this y square equal to x cube plus ax plus b. So if you have any power of y, so the even powers of, so y square you can replace by some function of x. So uh, anything you can write it as some function of x times y. So uh, we can write any rational function of r x y as some p1x plus p2x y. So plus y p2x by p3x plus y p4x. Pix are polynomial. So these are polynomials in, so these are polynomials in x. So any rational function, because whenever y square is coming, then and any even power of y, you can take this thing. So you can write in this form. Mm, even you can rationalize this. So this one actually you can rationalize by writing p1x plus y p2x p3x minus y p4x by p3 square x minus y square p4 square x. So now y square you can just put it in this form. So you can actually write it as some new q1x plus y q2x by q3x. So in the elliptic cup with this y transform, y square equal to x cube plus x plus b, we can write the rational function. So in this form, uh, we can write like this. Now given an endomorphism phi from ek bar to ek bar, so phi of xy is, so r1 xy r2 xy. So which are rational functions which you can write in this form. uh, so now so since phi is an endomorphism, okay, so phi of minus p is going to be minus of phi of p. So this is what we have. So so that means phi of so which is, okay, so phi of x minus y is going to be r1 of x minus y, r2 of x minus y. So so this is phi of okay, so and which is going to be minus of phi of x y. Okay, so
Sir, how you got it to be minus of pi x comma y?
you see, So the phi of xy is okay. So we know that phi is endomorphism. So phi of minus p is minus of phi of p. So phi of x minus y. So p is, if you write p as the x minus y, then minus p as x minus y, it has to be minus of phi of xy.
Okay, okay.
Yeah. So this is what I'm doing. Okay. So here, suppose R1 is in this form. And R2 is in this form, so can we say something? So okay, so if R1, so in this case, so if R1 is Q1x plus, so yeah, so this is just algebraic manipulations. Yeah, so yeah, minus of this means, okay, so let's see. So which is actually equal to minus of R1 xy minus of R2 xy. So yeah, so basically these two are equal. So R1 x minus y is same as R1 of x minus y. So if you write okay, yeah, so if you write, so if R1
Uh,
is
the
huh?
the phi xy point is on the elliptic curve,
Yes,
so its negative would only be the negative in the second point, no? Second coordinate.
yeah, negative is only in, yeah, so only in the second coordinate, that is fine.
So that should be minus r1. No, instead of minus r1, it should be r1.
No, you see, like remember that you see the endomorphism is given by a x, I mean given by this rational functions R1 R2.
Yeah.
But
So those r1
yeah,
r2.
yeah, so phi is endomorphism, we have phi of minus p is minus of phi p.
Yeah.
So yeah, so so that's why the phi of, yeah, so if p is p has coordinate x minus y, then uh, minus p has coordinate x minus y. So phi of x minus y has to be same as minus of phi xy. That's what I'm saying.
Yeah. Yeah. Not that part. I was asking about that minus p of xy. We have written it to be minus p of xy, as p of xy is our point on an elliptic curve.
Yes.
So its minus
Hmm.
should only have a negative in the second coordinate, not in the first, right?
Yeah, right. Yes.
So phi of xy is our r1, r2.
Hmm.
So minus phi
Why?
of xy will be r1 minus r2, r1 comma minus r2.
Yeah.
Why
So
x coordinate cannot be negative?
uh, as per our depth, if we take pxy,
Hmm.
p to be xy,
Yeah.
and then we know that minus p is our x comma minus y on
No,
elliptic
no, no.
curves.
Yeah. So p as a coordinate. So you see,
Yeah. So
p,
even phi xy
suppose
has
p is
yeah,
xy implies that minus p is x minus y.
x minus y.
So this
Yeah.
is okay, right? Yeah.
Yeah. Now our phi xy is r1 r2.
Yeah. So
So minus p
no,
xy.
yeah. So what is phi of xy? So given any x and y, phi of xy is given by the given by R1 of R1 R2. Okay.
Yeah.
So
So
so that
the
means now if
and
you replace y by minus y, then here y here is replaced by minus y. That's what I'm writing. So y here is
no, sir, below the step below.
yeah. So
You are writing.
yeah. So
Yeah.
this now phi of x minus y has to be equal to minus. Okay. So,
Yeah. So
so
this
phi of
part,
x
sir.
minus y is equal to phi of minus phi of xy.
Yeah.
Now because
Yeah.
of
That is
yeah, and
that is okay, sir.
yeah, so that means that's what I'm minus of the whole thing. So which I'm writing as minus of R1 and minus of R2. Is that a
But
confusion?
mine actually, sir, that is confusing with the because we are talking about on the elliptic curve. Our phi of xy is a point on elliptic curve, and
Yeah.
we are writing minus for it.
No, that is okay.
So
You see,
okay, and here we are doing the coordinate wise.
And the
We should go with the
comma
elliptic.
minus r2.
I see. So okay, you have a point,
Yeah.
right? So
Yeah.
Okay, right. So yeah, so yeah, let's see. So when I say minus, actually, yeah, so these are some like suppose phi of xy is x, yeah, so what, yeah, what Prabhakar is saying. So suppose p of p is some x1 y1, then minus of phi of p is going to be x1 minus y1, right?
Yeah.
Yes. So
So same would be applied for phi xy here, no? Because
okay,
xy
yeah,
is our point.
okay,
So
yeah,
only R2 will be negative in the step below. Yeah.
okay, yeah, right, you're right. So that's fine. Yeah, so yeah, so here is yeah, that's correct. So when we say minus, yeah, so this is how we are coming. Yeah, so because of this, now if R1 is, so in the right, Q1 x plus y Q2 by Q3, R1 of xy is same as R1 of x minus y. So this is Q1 minus y Q2 by Q3. So from here, from here what you get is that Q2 is actually equal to 0. Is that okay? Because Q1x plus y Q2x by Q3 has to be equal to Q1 minus y times Q2x by Q3. So from here Q2 has to be necessarily equal to 0. And yeah, so and if R2, so yeah, so so R1, so it's still right, I1 plus y Q2 by Q3, which then from here, from the y coordinate, so Q1 minus y Q2 by Q3. So here I'm like abusing notation. So this Q1 is coming, I mean R1 if I write in this form, then Q2 is necessarily 0. And if I write R2 in this form, then Q1 minus R2 of x minus y is Q1 minus y by Q2 has to be equal to minus of Q1 plus y Q2 by Q3, which implies that Q1 is 0. So yeah, so what we're saying is the following. So if you write R1, which is a rational function, in terms of Q1, Q2, Q3, then Q2 has to be 0 for R1 and Q1 has to be 0 for R2. So yeah, so that way, in that way, what we actually get is the following. Hence, phi of xy, phi of xy will be R1 xy. So R1 xy will be is Q1 minus Q2 is going to be 0. So yeah, Q1 minus Q3, so that means something like, so this is R1 of x and y of R2 of x for rational functions R1 R2. Okay, is that okay? Yeah, so though we started with this phi as a rational function, but the coordinate, first coordinate is just a rational function. The coordinate of x is just a rational function in terms of x, and other is y times a rational function in terms of y. And okay, so let's make it more precise. So let write R1x as, say, P1x by Q1. No, so this Q1 and other Q1 are, I mean, R2x as P2x by Q2x. So what we're saying is that in fact Q1 by Q3 or R1, then Q2 by Q3, yeah, Q2 by Q3 here is R2, but I'm just changing the notations here. Okay, so then phi of xy is in this form. uh, okay, let's see. Okay, so can I do it? Okay, yeah, so I want to say something. So if q1 of x is not equal to 0, uh, so here, so p1 q1, these are co-prime, these are polynomials, these are co-prime, p2 q2, these are polynomials, these are co-prime. So if q1 is 0 for some x, then phi of xy is the point at infinity, and yeah, okay, yeah, so that is fine. And if q1 is not equal to 0 for any x, yeah, yeah, so in that case, uh, yeah, in this case r2 is well defined in terms of, so r2 of x is well defined. Okay, yeah, so let me just open up this mark. So okay, so later I'm going to give you some exercises which will make it more clear. So well defined in terms of r1x. Okay, so that is fine. Okay, so now okay, yeah, so what we're trying to do is the following. I have an endomorphism, so we can define the map of the endomorphism. So the degree of the endomorphism, so definition, given endomorphism phi from e k bar to e k bar, define the degree of phi is the maximum of degree of p1 x degree of.
So what do you mean by Q1 non-zero, then R2 is well defined in terms of R1?
Yeah, actually, yeah, so I'm going to give an exercise which will make it more clear in the sense that you see the, yeah, okay, so the way we have defined this phi xy is that, so it's, I mean, given a point, yeah, so point on the elliptic curve, it gives another point on the uh, it gives another point on the elliptic curve, right? So now if q1 is not, I mean, this is q1 is not equal to 0, so phi1 x by q1, so this is the x coordinate of that point. So the y coordinate x is actually coming from the so y coordinate, so it's going to coming from the, by using the x coordinate. So that's how it's, we just want to we define in terms of x only. So well, that's why I write is well defined in terms of this, the first x coordinate.
You mean to say like y R2x can is the equation in x, like something like that?
Yeah, so so basically, you see the way the equation, we have this equation, right? So y square equal, so once you have x, then y is more or less fixed. I mean, of course plus minus those things are coming, but yeah, so y is more or less fixed. So and we're writing this phi of xy is some rational function times y, and the y coordinate is y times some other rational function. So by writing this is in this special coordinate form, so I'm going to give an exercise. So maybe in the next lecture, so in the next lecture I'll give some set of exercises which will make this make these things more clear. So yeah, so this maximum if the degree, if phi is non-trivial. So non-trivial means not identity. You see the, yeah, you can yeah, so not I mean like phi functions, so phi of p going to this yeah, so remember, if I ask you to give me an endomorphism, then you can still give identity function or the every point going to the point at infinity. So the function which takes every point to the point of infinity, this is trivial. So when it's non-trivial, then you define in the yeah, so no, yeah, when this is non-trivial, you define the degree of phi to be the maximum of degree of this rational function, polynomials giving the rational functions R1. Okay, so if so phi is actually 0, so phi 0 means the trivial, right? So I mean trivial in the sense that it takes everything to the identity. So then define degree of phi to be 0. So another definition. So here I'm just defining him because since the endomorphism is given by a rational function, so I'm just defining a map. So definition, so phi is phi not equal to 0 is called separable endomorphism. If so derive, okay, yeah, so you remember this R1, derivative of R1 dash is not identically 0. Yeah, so yeah, so if the derivative of the rational function R1 dash is not identically 0, yeah, so then phi is called separable endomorphism. So recall that you see R1 of x is Q1 of P1 x by Q1 of x. So yeah, so yeah, so this differentiation is not 0 means Q1 is yeah, so Q1 is not identically P1 and Q1 are not identically 0. So this R1 dash x is Q1 P1 dash minus P1 Q1 dash by Q1 square, right? So so that is both P1 dash and Q1 dash are not identically 0. Identically 0. Yeah, so for example, if P1 dash is 0, Q1 dash should not be 0, and vice versa. Okay, so let's see this with an example and try to see example. So the example which we have taken is, so phi of p is 2p. So that is phi of xy, we have written it as, okay, I just want to go back. Okay, so where is that? So this one, 3x square plus a square minus 2y. So this I'm just copying once again, so let me write down. Three x square plus a by 2y square minus 2x, then 3x square plus a by 2y okay, so here 3x minus 3x square plus a by 2y whole square minus y. So here I need to write this as a rational function, right? So how we're going to do is that, so you have this 3x square plus whole a square by 4y square. So y square x cube plus ax plus b, right? Okay, so yeah, so the r1 of x, so r1 of x is going to be 3x square plus a whole square minus, so 2 yeah, so by four y square, so 4y square minus so y square, you write it x cube plus ax plus b minus 2x. Yeah, so this one you're going to write it in the form p by q. So if you so if you rewrite this, actually, then so you get so 3x square minus 8, so it's going to be x power 4 minus 2ax square plus 8 bx plus a square divided by 4 x cube plus ax plus b. Okay, all right, so so this is so and you have to see whether there's a common factor here. So the one can see that there's no common factor, so the maximum of the, so this is p1, so this is actually equal to p1x by q1x. So degree of phi is actually 4. It's the maximum degree of maximum of 4 and 3, this is 4. So is that okay? Now we have to see whether this is separable. So yeah, so okay, so what is r1? So phi is separable since the p1 dash is not identically 0. If this identically 0, can it be, so 4x cube minus 4ax plus 8 4x cube minus 4ax no, p1 dash, okay, plus 8b and q1 x is 4 3x square plus a. So both of them cannot be simultaneously 0, identically 0, right? So yeah, so because of that this is not, yeah, so the thing is that we have to be little careful. So if characteristic of the field is 3, then this part will be 0, and then A is going to be, so if A is 0, Q1 is going to be 0, but then if the characteristic is 3, so the P1 cannot be 0. If the characteristic, of course, when characteristic of 2, if the characteristic is there, then both are identically 0. So but then this form is not in characteristic 2, so that's what we need to see. Okay, so phi is separable when characteristic of k is not equal to 2. So let's try to see what happens when characteristic of 2. So let characteristic of k is 2. So in that case, what actually happens? So
Sir, can you go to the definition of degree?
okay, so you have an endomorphism phi, then you are writing this phi as r1 times r2, right? So phi of xy is r1 r2, which we have written as r1 x y r2 x, where r1 is a rational function of the form p1 by q1, r2 is of the form p2 by q2. So the r1 is p1 by q1. So the maximum of the degrees of p1 and p2, this is the degree of phi.
Sir, how you got degree to be 4 in the example?
Yeah, so the thing is that the phi function is given by this polynomial, right? So r1 is 3x square plus a by 2y square minus 2x. So which you can write it as, like, since y square is this, so 4y square you can write it as 4 times this. So then you have this polynomial, this of degree 4 by degree 3. So you call it you say we have to have p1 pq1 to be co-prime, and one can see that these are actually co-prime. You know this. Yeah, so
No, I mean to say like degree of P2 can be greater than 4, right? Means like,
no
yeah.
degree of, no we're not going to p2, like other side. So we're just concentrating degree of r1. I'm not looking at the degree on the other side. So this is capital R1, which you can write it as R1 of xy, so depending on x and y, which you write it as a function in terms of a rational function in terms of x, which you get it. So I'm not going to the degree of the other part. So the degree of the first part, that's how we define the degree of the R1. Is that okay? But no, if I look at, on the other side, then of course, if you can do this, then it will change. But degree is only considered from here.
Are you saying degree of map is considered through R1 or degree of R1?
Yes. So degree of the map. So you see, given an endomorphism, define the degree of the endomorphism is the maximum of the degree of. Okay, so maybe I'll have to. So given an endomorphism, you can write in the form r1x y times r2x, where r1 is a rational function, which you can write it as p1 by q1, where p1 and q1 are polynomials which are co-prime, and r2 also, y p2 q2 are p2 and q2 are co-prime polynomials. So the degree of the endomorphism is defined as the degree of maximum of degrees of p1 and q1. That's what that's how we define the degree.
Oh, it's maximum
Actually,
of P1 and Q1. Okay.
you
Okay.
have
P1,
accidentally written
okay.
P2
I
there.
see. Okay, you have a point. Okay, I made a mistake. Okay, so sorry about it.
Okay.
Let me just see. Okay. So, yeah, I should have. Sorry about this. Yeah, so okay, this is how. Okay, thanks. Okay, I should have done. Yeah, I was telling P1 Q1 but wrote P1 P2. Okay, that's mistake. Okay, all right. So yeah, okay, so this is fine. Now in case of characteristic, no, so in characteristic 2, so we have to say something. In this case, you have this, you remember that y square equation is of the form y square plus xy is is actually x cube plus a 2x square plus a 6. Yeah, so here doubling phi of xy is actually given by uh, this. Yeah, so if you write the doubling in this form, so you want to write r1x, so let me just write then r2 of xy. So we won't go into r2 part. So r1 of x, the x coordinate of the doubling is actually, you can write it as x4 plus a6 by x square. So the degrees is still 4, so degree of phi is still 4 because the maximum of 4 and 2 is 4. And yeah, so which you write it as p1 by q1. Now p1 dash of x is 4x cubed plus a6, which is a6, and q1 dash is 2x, which is 0. Yeah, so both can be identically 0 unless a6 is okay, yeah, so I made a mistake here. So yeah, because a6 goes so 4x is 0, which is 0, q1 dash of x is 2x, which is 0. So here both p1 and q1 these are identically 0, hence phi is not separable. So phi is not separable. So this is just, I mean, later on we'll define so-called division polynomials where this separability is going to come into picture. That's why right now you may not appreciate it much why we say separable, but but when we go to these division polynomials, which are quite important objects, it's going to be useful. Now characteristic to two, we have two forms. One form is there, another form is y square plus a3y is equal to x cube plus a4x plus a6. So in characteristic polynomial, Weierstrass form is either this form or this form. So in this case, phi of xy, so doubling point is given by say r1x, r2 of xy. So here where so we can see so the doubling point, the coordinates are actually given by x4, sorry, x4 plus a4 square by a3 square. So here, so the degree is 4, right? The degree is 4, degree is 0, so degree is 4, and p1 dash also is both are 0, so this implies that phi is also not separable here. So in case of characteristic 2, so endomorphism given by phi of p is 2p, this is not separable. So I want to have a remark here. Yeah, so later on we'll prove it. So if P is say PP, where okay, so here P is the characteristic of K. Okay. Then so we need to actually degree of phi is actually P square and is not separable. Alright, so this comes from the theory. I mean, when we have this state division polynomials, but yeah, this is what I want to say. So another definition which is very important.
Sir, what have you written in the first line?
Okay, so if phi of P is P times P, so the instead of doubling, so K times P, right? K is equal to P here. So you're adding P times. Is it not clear? So you remember that phi is a map from EK bar to EK bar. So P is going to P, yeah. So here P is the prime P and this capital, maybe I should write Q going to, okay, so Q going to PQ, where P is the characteristic of the field K. So as such, endomorphisms are just, I mean, maps, homomorphism from the group homomorphisms of EK closure to EK closure. So here we can define the degree and separability. So that's the thing. Now another important this endomorphism is Frobenius endomorphism. So Frobenius endomorphism, you see the map which takes in a field you might have seen, or in a finite field or field of characteristic P, the map which takes x to x power P, this is called a Frobenius homomorphism, right? So here, so we want to define something like this. Of it's the map given a phi of x and y is equal to x power P, y power P. Here K is okay, so characteristic of K is P. In fact, okay, so maybe I'm going to just take it more precise. So let K, okay, so let K is the finite field, so that characteristic is P. Then this is called yeah, so then endomorphism phi of xy is called Frobenius endomorphism. So yeah, so one can check that is it here R1 is x power P, R2 is y power P, and we just write phi of P. Okay, so to be on the side, so P of P, and when we consider this fine okay, so maybe I won't just write Q, so let me make it more fine. Yeah, so not only finite field P but any finite field. So remember that if Q is a prime power, so here Q is power of P. So if for any prime power, so finite field of Q elements is of characteristic P, which is a finite extension of FP. Then in this case, the map which takes xy to x power P, y power P, this is called the Frobenius endomorphism. So here I just want to, before I state this proposition, I want to prove the state and prove the following lemma, which is, so here from here what you can see is that the degree is going to be P. So degree of the Frobenius endomorphism is P. That You can clearly say.
Sir, how is it clear? Like it sent point of elliptic curve to point of elliptic curve. Like, is it?
Uh, yes. So, yeah. Okay. So, yeah. So the question is that, given, okay. So that's an interesting, yeah, question. So let's, before I write the lemma, let's do it. So we have this y square equal to x cube plus ax plus b, right? So
Yes.
yeah. So yeah. So given xy now, x power p, y power p is going to be this thing. So yeah. So let's see. Now if you replace x by, sorry, so x cube, so x power,
Okay, sir, got it.
you got it? Okay, okay. Yeah, so yeah, you can tell for the others. So I mean, when you say you got it, so you can tell so the others know.
So basically, we can take the y square power p,
Hmm.
which will be equal to the x cube plus ax plus b power p,
Yeah,
which will be xp power p plus a
yeah.
x x power p plus b.
Yeah.
So basically, it will satisfy the equation.
Yeah, that's true. So b power p is actually b, a power p is actually a. So that's what. So is that clear to everyone? So when in case of finite field or field of characteristic p, the taking p power is very simple. So you just take the powers of the individual terms and then that's all. Okay, so yeah, and that is fine. So now let's write a lemma. Sorry. Let E be an elliptic curve over FQ prime power field. Okay, so Q is prime power. Then okay, yeah, so 5p. Okay, so okay, so yeah, so I also I think I missed something. So not only p, but you can I'll just come back in a second. Okay, so yeah, sorry, there was so you can have actually not only the p.
Sir,
Oh, yeah.
related to last question, like So basically, we wanted it to be endomorphism, right?
Yeah.
For k equal to fp, it's clear to me.
Yes.
For fq, how it would work?
Okay.
Okay.
So
Okay.
you can still do the same thing. It doesn't change. You see the way you have said, right? So y square equal to x cube plus ax plus b, right? So yeah, so if you take power q, in fact one thing is that q is p power, you can keep on taking p. Yeah, so if you do like that, then basically we have some issue. So what you do is that you take this first p power, which will get yp whole square is x 3p plus a xp plus b. Yeah, so then you take one more p power, you keep on taking powers of p. Is that okay? Till you come to q. So if you take p power, then it will become 3p square plus ax 2p. Then yeah, so by induction you can do that. Is that okay?
Yeah, it's
So yeah, so this one we call it the okay, so the Frobenius endomorphism. Then let's consider an elliptic curve with a Fibonacci, over FQ. Then Frobenius indo is of degree, of course, Q. This is quite clear, and but this is something not very clear, not trivial. So but figure is not separable. See, yeah, not separable, so it's quite clear. If you take this p1 q1, so if you can also do you can also do the same thing. X is x power q, it is p1, and q1 and q1 is just 1, so both are identically 0. So that's so that also makes it separable. But okay, so first we need to show that. Okay, so so first of all, it's clear that you see, if given x y a point on the curve x q y q is a point, that is now to show that this is a endomorphism, we need to show the additivity of 2 points. Okay, okay, so suffices to prove endomorphism, that is phi q of p1 plus p2 is phi q of p1 plus pq of p2. Okay, so okay, so we need to show that actually this is endomorphism. The rest is clear. Once it's a endomorphism, then the rational functions already yeah, so degree has to be q, and if you write this p1 by q1, both are identical. The differentials of both of them are identically 0, so it's not separable. Yeah, so so this is also pretty simple. So let x1 y1 x2 y2 in e power FQ closure with x1 not equal to x2. Okay. Let x1 y1 plus x2 y2 equal to x3 y3. So here we have to show that this under this map their sums actually go, yeah, so yeah, sum also satisfies this. So it's more of algebraic manipulation. So so I won't go it completely, so I just want to tell you. So here the slope joining x1, so write m as so the slope joining is y2 minus y1 by x2 minus x1. So then x3 is just simple, so m square, we have seen x1 minus x2. Y3 is m x1 minus x3 minus y1. So yeah, so this one we have seen before from the addition properties. So yeah, so now you raise it to the power, I mean, so yeah, so this x3 power q is going to be yeah, so m square power q. So yeah, so this one I'm just going to write it m square 2q, you write it as m2q minus x1q minus x2q, and y3q is going to be m prime x1q minus x3q minus y1q. Yeah, so okay, yeah, so the thing is that y is going to be m dash, so here m dash is actually equal to y2q minus y1q by x2q minus x1q. So yeah, so if you take this m, yeah, so m to the power q, then actually you're getting y2q minus y1q, x2q minus x1q. So nothing changes here. So from yeah, so this tells you that phi of p1 plus phi of p2 is actually phi of p1 plus p2. Yeah, so actually, so we're doing it. Yeah, so this is the first time when we are doing it x1 not equal to x2. So we can do some similarly for this when x1 is equal to x2. So which I won't go to similarly for x1 equal to x2. When x1 equal to x2, in that case you have this the slope is given by the tangent, and then the slope of the tangent, then you are done, right? So once we do it, we can prove the following, yeah, so following proposition. So what we have, so among all the important, among all endomorphisms, one of the important endomorphism for finite fields is this Frobenius endomorphism, which is of degree q and which is not separable. Okay, so let me just stare and put the following proposition. So why we're introducing this separable endomorphism, the following. So let phi not equal to 0 be a separable endomorphism of E over K. So E is the elliptic curve defined over K. Then one is the degree of alpha is not, so degree of phi is actually equal to the number of elements in the kernel of phi. Okay, so yeah, so remember that phi is a map from ek bar to ek bar. So the kernel of phi is the kernel of this homomorphism. So yeah, so this is homomorphism. You look at the kernel, and degree of phi is nothing but the kernel of this homomorphism. And what happens if it's separable? So if phi is not equal to b is non-separable, is not b is not is non-separable, then degree is strictly, so degree of phi is strictly less than the coordinate of the kernel. Okay, so yeah, so this is interesting. I mean, this is the point which tells you why we consider this separable and unseparable. Okay, so now let's go and get a proof. The proof is, I mean, simple, and but this is important. So let me just give the proof. So write. Okay. Okay, so remember that. Okay, so when now see this with the Frobenius. So the Frobenius one is not separable, and degree is q. And what is the kernel here? You see in this lemma, you see this is not separable. So degree is q, and the kernel of this endomorphism is, I mean, the coordinative kernel is just 0, right? So it's 1. I mean, kernel is just 0, so current is 1. So q is definitely bigger than 1. Okay, so write phi of xy as p1x by q1x. So y r2x. Okay, so and so that you already know. So degree of phi is the maximum of degree of p1, degree of q1. So let me just go back a moment. I think separable. Okay, so the separable is not identically 0, right? So let phi be separable, so that r1x, which is not equal to 0, which implies that p1 dash q1 minus pq1 dash is not identical, not a 0 polynomial. Okay, so let S be the set of all x in k bar such that p1 q1 dash minus p1 dash q1 of x times q1 of x is 0. So let okay, yeah, so maybe instead of writing, so let AB belongs to E of k bar. So I'm going to define some set. So let's let AB be element on the field k bar such that A is not equal to 0, B is not equal to 0, and AB is not a point at infinity. Okay. Second property is that degree of p1x minus a q1x is maximum of the degree yeah, so maximum of degree of p1 yeah, in q1, which is just alpha. Okay, so degree of phi. So I'm taking AB points us that degree of p1x minus a q1 is same as the degree of maximum degree of p1 and q1, which is degree of phi. The third property, A is not in. Okay, so here R1 is P1 by Q1. So R1 is A is not in R1 of S. So yeah, so remember that R1 of S means this R1 of X such that X is in S. Right? So this is R1 of S, and AB, this is in the phi of EK bar. Yeah, so phi is an element. Yes, yeah. So
Point 2 will hold always, right?
you see, no, not necessarily, right? If, for example, if the maximum degree is q1 and if A is 0, it won't be true.
Okay. But we have assumed A to be non-zero, so
Yeah, okay. Yeah, right. So A to be non-zero, so that is fine. No, I think so. Like for example, if P1 and Q1 both have the same degree, and the leading coefficient of P1 is A, like suppose if you can find some such that the leading coefficient they can cancel out. So most likely, I mean, this not
we have P1 and Q1 to be co-prime, so that is also not possible.
No, P1 and Q1 are co-prime. That is okay. Like for example, x square plus 1 and yeah, so x square plus 1 and 4x square plus 3, they're co-prime, right? You see, when we say co-prime, we're co-prime over the field K, not over the ring. So yeah, so x square plus 1 and 4x square plus 3, these are co-prime. Yeah, but then
Can you explain again? I missed it.
like, so this one x square plus 1 and 4x square plus 3, are these co-prime? But these two polynomials are co-prime.
Yeah, I guess. Yeah.
So if I multiply by, now maximum of degrees is 2, if I multiply by here and subtract, so I'm just giving an example. So in that case 1 minus 3, so minus 2 is equal to minus 2. So if you difference of the degree is 0. Okay, so yeah, so most likely this is, I mean, going to be true for almost all, but I mean, we want to avoid these cases when these kind of things come up. Okay, so first I'm taking set S to be set of this yeah, so set of points. So now first of all, S is finite, that all of you agree, because P1 Q1 minus P1 just Q1 X. So this is product of two polynomials, and there are at most finitely many roots of this polynomial. So S is finite. Yeah, and yeah, so S is finite. Since this P, okay, so yeah, so because of the fact that this this is not identically zero, the set S is finite set. So yeah, so since P1 Q1 prime minus P1 prime Q is not identically zero and Q is not zero, yeah, so S is finite set. So that is part is clear, which implies that phi of S is finite. Well, when I say phi of yeah, so phi of S means, you see, yeah, so this is a little bit misleading. Okay, so I just need to make sure that okay, so yeah, so you have this S, so phi of xy with x in S is finite. So that's what I mean. So S is finite, so if you look at all those xy, phi of xy with x in S, so this set is finite. But if you, what is this phi of xy is r1 of x, y r2 of y, yeah, and r1 of x okay, okay, let's see. Yeah, so this point, so what is r1 of x, which is p1 of x by okay, so can you take infinitely many values? So r1 of x and can you take infinitely many values? Okay, so x now takes infinitely many values for x in k bar, for x in for, so you see, when x runs over the algebraic closures, then r1 can take infinitely many values, because this is not identically zero, so it can have infinite, I mean so p1 is derivative is not identically zero, means not a constant function, so it takes infinitely many values. Now for is x in k bar, implies that there exists y such that there exists y such that y in k bar such that xy is in ek bar, right? So in ek bar, given x, there exists y such that ek bar. So and this r1x takes infinitely many values. So this implies that phi of ek bar is an infinite set. Okay, so I want you to understand this a little bit better. So phi, I have phi already. It's now since phi is a non-constant so phi is non-zero. R1 is non-zero. So if you take this algebraic over algebraic cross, it can take infinitely many values. And also the fact that given x in k, you have x in k bar, there exists y such that xy is in ek bar. So yes, for every r1 you can have this another point such that that's also point on the elliptic curve. So in particular, phi of ek bar is an infinite set. And since ek bar is an infinite set, now you go to AB. So there can be at most finally many AB satisfying, which doesn't satisfies this. So now this comes to one of your questions. So there can be at most very few A for which degree of P1x minus is not equal to degree of phi, and yeah, so yeah, a not in this yeah, so and very few A's that R1 of A, yeah, so R1 of A is in R1 of S, and yeah, so from this fact, from this remarks, what we know is that AB, such an AB exists. So hence such AB exists. Okay, so yeah, so yeah, now yeah, so once such an AB exists, so we have to show that there exactly this degree of 5 points such that yeah, so satisfying this. So what we want to show is the following. So the claim, there are exactly degree of phi points x1 y1 in ek bar such that phi of x1 y1 is AB. Yeah, so what we're saying is that AB is coming from exactly degree of 5 many elements. Yeah, so yeah, so that means for such a point, okay, so this is our claim. So for such a point, what we have is the following. So phi of xy is AB means A is actually P1 x1 by Q1 x1, B is y1 times so R2 of x1. Okay. Okay, now this AB is not a point at infinity. Yeah, so which implies that Q1 x1 should not be 0. All right, so yeah, so far we have this. Now once q1 is there, so r2 is defined now. So since b is not equal to 0, y1 r2 x1 is equal to b, implies that y1 is b by r2 of x1, which are non-zero. So q1 is not equal to 0, and yeah, so r2 is defined, so then y1 is b by r2 x1. So yeah, so which implies that, so which implies that y1 is determined by x1. So yeah, so to prove the claim, we need to actually count the number of such x1. So to prove the claim, needs to count the number of such x1. Okay, so this is what we have. So let's try to do that. So now what was our second assumption? Okay, so I just go to that. The second assumption is that degree of p1 minus aq1 is the degree same as the degree of phi. So we'll go to that. Since degree of p1 x1 okay, so no, here not x1, so x minus a q1 x is degree of phi, which is the degree of maximum of degree of p, and so yeah, so since this, so there are, so this is of degree, so there are exactly degree phi roots of this equation. There are degree phi roots of p1x minus a q1x equal to 0. So but some of the roots may be multiple roots, so I want to make sure that this doesn't have multiple roots. So to show that it doesn't have a multiple roots, so a root should not satisfy both this and its derivative. So p1x, so p1x minus aq1 should be something 0, then p1 dash minus a q1 dash equal to 0. This should not be possible. So let's suppose that, so let x not be a multiple root. So if it has a multiple root, what happens? So then p1 x naught minus a q1 x naught is 0, which is same as p1 dash x naught minus a q1 dash 0, not 0, x naught. Okay, yeah, so I want to sort of get this. So p1 x naught is a q1 x naught. Yeah, so you multiply, multiply with this, yeah, with this, and multiply with this, so both should be same. So what we have is that a p1 x naught minus so q1 dash x naught should be equal to a p1 dash x naught q1 x naught. And here n a is not equal to 0, so we can take out a. So that means q1 dash x naught, okay, yeah, so just a sec. Okay, so so this is what we have. So that means p1x into q1 dash x naught is same as p1 dash x naught and q1 dash so q1 dash x naught. So so that means derivative of p1 q1 at x naught is 0, right? So so this implies that x naught is a root of p1 q1 dash minus p1 dash q1. Yeah, so if there's a double root, then x naught is a root of this. So now so remember that what is s. So s is the set of all x's, that x is a root of this times q1. So that means, so this implies that yeah, just a sorry, actually there was a lot of this thing. So x naught is the root of this, so that means x naught is in s. So once x naught is in s, but then we're taking, remember that so we're taking s, I mean we're counting the number of s1. So okay, so if it's a multiple root, so s, then a, which is r1 of x naught, which is in r1 of s, which is a contradiction because a is not in r1 of s, so which is a contradiction. So thus this so thus p1x minus aq1 equal to 0 has no multiple roots. So hence p1x minus a q1x has degree of phi roots, distinct roots. Okay, so far we have got this. Okay, so since so now this has degree of phi distinct roots, and so since they're exactly phi, okay, so exactly degree of phi points x1 y1 such that phi of x1 y1 is actually AB, kernel of okay, so kernel of phi has degree phi elements. Okay, so I want you to understand this. So remember this. So when to see the kernel, yeah, so the kernel, how many elements are there in the kernel? Yeah, so for AB I have exactly phi, degree of phi, yeah, so phi points. So what we have, okay, so let me just come back to it. So we have claimed that there are exactly degree of phi points x1 y1 such that phi of x1 y1 is AB. So far we are claiming it. So yeah, so once we have claimed that, our aim is to show that kernel of phi has degree phi, yeah, so degree phi elements, right? Okay, so let me see, is there anything? So okay, actually degree phi points such that phi of x1 y1 is AB. Yeah, so that is correct, so that's fine. So because AB is a point, so yeah, now since phi is a homomorphism, by using the property of homomorphism, actually you can really see that the kernel has to have exactly, since they're at exactly degree of phi elements satisfying the, so the kernel of phi has to have exactly degree of phi elements. So since, okay, let me just, since phi is a homomorphism, so endomorphism means homomorphism, so AB in EK bar, so for, okay, so maybe I'll just, for AB in EK bar, they're exactly degree of phi points x1, so points x1 y1 yeah, so x1 y1 with phi of x1 y1 is AB. Okay, so okay, yes, so this proves, so hence okay, so yeah, I think, okay, we are, okay, let me just see. Okay, yeah, so I think yeah, this completes the proof, but let's try to start from the beginning to make sure what we're trying to see. Okay, so let's look at the proposition. What is the proposition? Suppose phi is a non separable endomorphism, then we have to show that degree is same as the kernel of phi, right? If it is non-separable, then degree should be strictly bigger than kernel of phi. Okay, so to do that, what we are doing is the following. We started with this, remember that once is separable, p1 dash minus q1 minus p1 q1 dash is non-zero. So you take s to be set of roots of this polynomial times q1x. Then we try to find, yeah, so n AB which satisfies, I mean, which doesn't involve any of the roots of this, and for which degree of p1x minus a q1x is same as degree of phi. then what we say is the number of roots of then number of roots of here same as degree of phi, and we proved that there are exactly degree phi points x1 satisfying phi of x1 y1 is AB. Okay, and so this implies and actually to do that to do that we actually work out with different properties and different manipulations, and we saw that this p1x minus aq1 has exactly degree phi distinct roots, and which gives that there are exactly phi of degree phi points x1 y1 satisfying this. So so this tells you that kernel also has degree phi elements, because the kernel has more than degree phi elements, then phi of x1 y1 equal to AB will have more than degree phi elements.
Sir, can we stop? We have class from 4.
Okay, so what time is it now? I think so we'll stop now. So I'm going to share, so the things I'll just stop in a moment. Okay, so this completes the proof, so I'll just but I didn't say anything about this non-separable. So just one, if phi is non-separable, so P1 so P1 dash minus a Q1 dash could be identically 0. So that means many of the arguments may not work here, so that's why this thing doesn't work. And by looking at the arguments, modifying the arguments, we actually get the result. So, and result obtained by modifying arguments. Okay, so I'll stop for now. So I'm going to share the so I'm going to